Hey folks, I wanted to give you a little instructional video to let you know exactly how R is calculating these p-values and these confidence intervals. So as we start this week, and even into last week, we learned a lot about what goes into these hypothesis tests and kind of the basics of confidence intervals. And this week we're going to focus more on um, how to actually calculate those things in R, but I wanted to give you kind of a rundown of what R is actually doing to calculate those things. In a typical statistics course, similarly, something that's not just 8 weeks long, we would probably do this by hand at first and then rely on technology. I felt for a course like this, it would be a little bit easier to focus in on just getting those values out of R without worrying too much about where they came from. So this video will kind of give you at least an idea of where they come from. It's not just some sort of magical being inside of R producing fake numbers. So for a p-value, we calculate a sample statistic, a point estimate. So typically what we've been talking about so far is something like x bar or p hat, whether we're working with a sample mean or a sample proportion. We're going to take either x bar or p hat and we're going to transform it into what we'll call a z-score, and I'll usually just abbreviate that z sub s, or a t-score, t sub s. And both of these have formulas that we can get into, but generally all we're doing, for example, with the t-score formula, is we're going to take x bar, we're going to subtract from it our hypothesized mean value, and we're going to divide by the standard error of x bar, s over the square root of n. What that's going to do is we have some assumed distribution, a normal distribution or a t-distribution, based on whether we're working with a proportion or a mean, which you should have been reading about. And this t-score or z-score is basically going to take that assumed distribution that we had under the null hypothesis, and we're going to shift it so it is centered now at 0. So whatever our mean was, our mu, our true mu, or our true p, we're now centering our test at 0. So we have this distribution. It is now centered at 0. And I'll just work with the means example, although it's the exact same thing if we're working with a proportion as well. We will use that z-score or t-score, and that t-score is going to have a home somewhere on this distribution. So let's just say, for example, we have a t-score equal to 3.4. So our t-score is going to be somewhere maybe over here in our distribution. The p-value that we're going to get out of R based on this t-score is going to be the shaded area under the curve that is greater than or equal to our t-score. So this here is going to be our p-value. So, to actually calculate this p-value, we would need to know a little calculus. Shade of, or area under the curve is what we use integrals for. I don't want you to have to worry about calculating any sort of integrals for this course. And more generally, most people don't actually do the integral calculations. They go to a website or typical statistics textbook has tables already for kind of these general t-scores that you may see. So if you're interested in that, you can Google a t-table or a z-table, and you'll kind of see what I'm talking about. But that p-value is just representing the area under the curve that is greater than or equal to our observed value. So when we talked about p-values, and when I introduced them, I said that a p-value is the probability of observing our sample or a more extreme sample, given that the null hypothesis is true. We're taking our sample, our observed sample, and we've got it represented here in this t-score. And we're kind of basing it on, if the null hypothesis is true, what's the probability that we would observe this t-score? And that p-value then, the shaded area, represents that probability. We determine what side we're looking at based on our alternative hypothesis. So let's just say, for instance, if we have some mu and we're interested in showing that some mu is less than some value mu naught, what I typically recommend then is we can take this less than sign and make an arrow out of it, and that tells me, when I'm looking at my distributional table, that I'm going to be looking at the shaded area to the left of my calculated t-score. We could do the same for a greater than sign. That means we'd be looking to the right. And if we have one of those crazy not equal to signs, it doesn't really lend itself to making a great arrow, but that just means we're going to be interested in now both tails. So similarly, when we're talking about confidence intervals, we have the same ideas at play. So we know a basic formula for the confidence interval is some point estimate plus or minus some distributional value times the standard error of our point estimate. So for example, if we're working with a mean, our formula would be x bar plus or minus the t distribution value times the standard error of x bar, which we can represent s squared over n. You might also see it as s over the square root of n, same thing. This t value typically will have a little subscript on it. We could do 1 minus our confidence level, CL, divided by 2. And I'll explain what that means in a second. So what this formula is saying, or how we can get those distributional values, is we again have some assumed distribution, normal distribution or a t distribution, and we have some confidence level, and we are partitioning this distribution based on our confidence level. So everything here is going to be 90, or whatever our confidence level is, percent of our distribution is going to be covered. And then our mark-off spots are going to be those distributional values that we are going to use for our formula. So that leaves the corners. What's remaining is this 1 minus CL over 2 in both of these edges. One thing to note, 1 minus CL is the exact same thing as alpha. So actually it's alpha over 2. So we're leaving alpha over 2 in both of these non-shaded areas, which is going to tell us then what the t-score would be, or z-score would be. Maybe not even score, but just the distributional value to use in our confidence interval calculation. So we want to make sure that whatever our confidence level is, maybe 95% of our distribution is being covered by our confidence level, and we can figure out what values would be represented in our given example based on these t values here. So I hope that kind of clears some things up. Again, R is going to be calculating these things for you, so you don't actually have to worry about digging out any old stat books and going to any tables online and finding those values. We're going to let R do that busy work. But sometimes R does become a black box, and so hopefully this kind of led you into a little bit more insight about what R is actually calculating. If you have any questions, please don't hesitate to post to Blackboard or send me an email. Have a good day, and I'll talk to you soon.